Well, welcome everyone to our first distinguished seminar for the ACTION Institute. Just in a sentence, ACTION is an NSF-funded AI institute that started on June 1st of last year. So we're approaching a year of life, not yet, but almost. And as part of the institute, we have a fantastic student council that help us sort of like understand the issues that students are interested in and they care about. And this group has invited Nicholas Carlini for this lecture. So I'm passing the baton to Shinan, who's the head of the student council, and will introduce our speakers today. Thank you very much.
Yeah, thank you, Professor Vigna. Yeah, hi everyone. I'm Shinan. I'm head of this ACTION Institute Student Advisory Council, and I'm also like a final year PhD student from University of Chicago. Today, we are thrilled to have you join us for a webinar on making adversarial ML practical with Dr. Nicholas Carlini from Google DeepMind. So as Professor Giovanni Vigna said, yeah, this ACTION AI Institute is comprised by 11 universities across the US, and it is led by Professor Giovanni Vigna as well. Yeah, each quarter of the year, we invite one distinguished guest speaker who works in the intersection between AI and security. So yeah, and the guest speaker is voted by us in the advisory council from ACTION. And for today, yeah, during the talk, feel free to post your questions in the Q&A session. And we will have a dedicated Q&A segment at the end where Dr. Carlini will answer questions for you. So before we begin, let me introduce our distinguished speaker, Dr. Nicholas Carlini. He's a leading research scientist at Google DeepMind, where he delves into the security and privacy aspects of machine learning. His groundbreaking work has earned him Best Paper awards at prestigious conferences like ICML, Usenet Security, and IEEE SNP. Dr. Carlini completed his PhD at UC Berkeley in 2018, and he has been at the forefront of research in adversarial machine learning for a long time. Yeah, his contributions to this field are not just like academically profound, but also pivotal in shaping the future of security and privacy-preserving AI technologies. So without further ado, I'm honored to welcome Dr. Carlini to our virtual stage. Yeah, please take it away, Dr. Carlini.
Thank you. Yeah, I'm excited to be here and talk with everyone. Let me get things going. Okay, slides are good. Okay, great. Yeah, so I'm going to talk about some work that we've been doing on trying to make adversarial machine learning practical. And the way that I like to think about this is, all right, so here's a paper. This paper was written in 2007. It's the paper that introduced returnative programming to the world of computer security. This is like one of the most important papers in computer security that like really changed a bunch of things. And it has, I don't know, what last time I put these slides together, 1,900 citations. And then if we compare this to like machine learning, like here's a paper that I wrote when I was a PhD student, you know, numbers look good, like, you know, 8,000 citations, yay. But if you actually look at what the impact of the work is on the real world, this returnative programming paper that has, you know, less than 2,000 citations, like has literally changed the way that we build software. The processors we use are different. There's like Intel and AMD have changed the way that they design their processor to make it possible to write software that prevents this kind of attack. Every operating system in the world, the Linux kernel, Microsoft has introduced operating system level defenses to this attack. All the compilers in the world have introduced compile time flags that make it harder to perform this attack. Like everything we do in the world is different because of this paper. But on the other hand, if you go back to these like adversarial example attacks that I've been doing for a while, not completely, but like for the most part, the impact is like almost nothing. Like no real production system that people are deploying today is built different because this paper exists. The best image models, the best classifiers don't take into account the fact that adversarial examples exist. They build exactly the image models they would have built otherwise. The best language models in the world don't take into account the fact that this attack exists. They build their language models exactly as they would otherwise. And so really what I'm trying to do is to say, like, by one metric, like adversarial machine learning like has lots of citations, which like scientists like to think of as impact. But we haven't really touched the real world. And so I think by that account, we've kind of failed as a field. And so what I've been trying to do over the last little bit is to change this. And I think the big question to me is like, why does this happen? And, you know, maybe sort of because I've been part of this community for so long, I feel a little less bad attacking ourselves. Like I've said to the people, like adversarial machine learning is the art of making up adversaries so you can write papers about problems that don't exist. Because like for a long time, just machine learning hasn't been effective. And so how do you do security in a world where you don't actually need to secure the systems? You say maybe in some future, there will exist someone who uses a model in this way, and then we can go and study what that potential future looks like. And so we make up these adversaries that may or may not exist with the hope that they will, because machine learning just hasn't been very effective for a long time. But like a couple of years ago, things changed. Like machine learning for a very long time just like didn't work well. And I don't know, pick the year that you want, but within the last couple of years, machine learning has just started to work. In every domain that for a long time we've said you can't do machine learning there, these machine learning models now just are really, really good. In the last couple of years, we've gotten really good at language modeling. Maybe a year before that, we got really good at image modeling, audio modeling. Basically, all of the classical problems of machine learning aren't solved, but like just they're definitely above the bar of do they work? And what that means is that now we no longer have to hypothesize potential ways in which machine learning models will be used in some future and then attack those hypothetical situations. We can now look at actual ways people are using machine learning today and try and attack those real systems as they exist. Okay. So this talk then is basically going to try and say, let's make these adversarial machine learning attacks practical. I'm going to do that in a few pieces. And the way I'm going to do this is I'm going to try and basically walk through each piece of how we train machine learning models and introduce a practical attack on that component of machine learning. So to get started, let's look at just how this pipeline works. So we start with some emails in this case, and we're going to pass them into some training algorithm. And the output of this training algorithm is going to be some machine learning model, some neural network. And then what we're going to do is we're going to, at test time, take some new example, pass it into the neural network, and ask, like, is this a spam email, yes or no? And the idea of adversarial machine learning is that we can attack each of these pieces of the training pipeline. And so what I'm going to try and do is walk through a way of making each of these attacks at least a little bit practical. And I'm going to start with poison. I'm going to try and start with a poisoning attack that we can actually implement in the real world. Okay, so poisoning attacks are a fairly simple kind of attacks. The idea is you want to modify the training data set so that the model performs poorly on test examples. These attacks have been known for a very long time. And you know, in fact, the poisoning attacks recently got the Test of Time Award at ICML a year and a half ago or so. And the basic observation is that these work in practice if the adversary has access to some control over the training data set. But like these papers here are being written on MNIST. You know, MNIST was collected in the 90s by the government. Like the government is not out to poison all of our training data sets. And even if they were, they had one opportunity to do this in the 90s and they can't modify the data set after that. And so really what I'm trying to ask for is there a way to make these poisoning attacks practical in some way that actually lets the adversary have control over the data set? Because like right now, essentially the only thing I can do for most of these poisoning attacks on like MNIST and CIFAR is like assume an adversary has access to a time machine and can go back in time and modify the data sets. And like, this is not a realistic adversary. And so what I would like to do is to try and come up with poisoning attacks that work in against like big real systems that we have today. Okay, so how do we do this? And this is a paper that's going to be presented at S&P in maybe 2-3 months. So let's talk about data sets people use for machine learning. And suppose that you wanted to train some state-of-the-art model. Like, what would you use? You know, if you were in the 90s, you might have trained on MNIST. Like, this was a hard data set 25 years ago, but for the most part has been solved for a very long time. So people just don't train state-of-the-art models on this. Same thing so far, you know, in the 2000s. This was a hard data set, but again, it's basically been solved. People don't train state-of-the-art models on SUPER. ImageNet, again, very hard data set, but we've mostly solved this. The best machine learning models on ImageNet are at or above human levels of performance now. So we don't really work on this too much. Instead, we use these data sets like Lion 5 billion or something like it, where these data sets have been constructed by crawling the internet and just collecting 5 billion images that people posted online, along with some kind of text description of the image. These are data sets that were used to train models like CLIP, the OpenAI image captioning model. They used to train diffusion models like Stable Diffusion. And so the ability of an adversary to control one of these data sets would actually impact some of the biggest data sets that we have, some of the biggest models that we have in practice. And so for this reason, like, this is really what the state-of-the-art people are using to try and train their best models. Okay. So this sort of begs the question. Suppose you wanted to use this data set, how would you actually distribute a data set with 5 billion images, right? Like, this would be pretty hard. And the answer is just like, you just don't distribute it. And there's basically 3 reasons why. The first is it's huge. This data set is, I don't know, 100 terabytes. It would be really expensive for someone to host a data set of 100 terabytes that anyone in the world can access. The second is just, I don't own the images. Is it even, am I allowed to host a copy of 5 billion images I don't own? Probably not, I don't know. And so people don't host them for that reason. And third, these are 5 billion images scraped from the internet without much curation. Like, who knows what kinds of content are in these images? And so I really don't want to be responsible for distributing whatever happens to be in these images. And as it turns out, there were a bunch of problematic images in this data set that there's some stuff going on about this right now. But for this reason, people really don't want to be hosting these images themselves. So what do? They say, okay, I'm just going to host a metadata file of all of the URLs that you should go download and all of the corresponding labels of what those images actually are. And then they provide a downloader tool for you. They say, here's like image to data set. You can go and scrape these images for yourself. And now at least the data set owners can have some level of being able to say, like, look, it's not on us if there are problems in these images. This doesn't resolve all of the problems, right? If there are problematic images, it's now on the people who are downloading it. They still have problems. But at the very least, the data set owners have, the data set curator has some level of being able to say it's not completely on us. And so this is what in practice people do. Okay. So this is great and everything, but there's a slight problem with this, which is that, the data set was probably not malicious when it was constructed. Like I know some of the people who built this, I trust them, they're good people, they're not out to get you. But when you're pointing to live URLs, who's to say the data set's not still malicious today? In particular, domain names expire. And when domain names expire, anyone can buy them. In particular, I can buy them. So anyway, I now own 0.01% of Lion. Anyone who has downloaded Lion in the last year and a half has come to my server and asked me for images, and I have politely refused to respond, but I could have done anything else that I wanted. Not only do I own 0.01% of Lion, I also own at least 0.01% of line 400 million, Koyo 700 million, conceptual captions 12 million, conceptual captions 3 million, PubFig, Space Grab, and VGG Face. So basically, if you've used any of the big models data sets that people have distributed over the last couple of years, you have explicitly trusted me not to sort of return malicious images to your models. And this sort of thing is a fundamental shift in the way that people have to think about these things. We're not introducing a new type of attack. We're just saying this attack that's existed for a very long time, turns out it's immediately practical. My server literally has a "does Nicholas feel evil today" line of code that currently is false. And because it's false, I just return a 404 for any time someone queries me. But in principle, at any moment, I could set it to true and start returning poisoned images to anyone who asked. And we get thousands of requests a day, millions of requests a year at least, for these images. And so we could poison lots of the biggest models. And we don't, but I think this sort of is a shift in how we have to imagine poisoning in the future. It's not the case anymore that today we can rely on the fact that it's just not possible to construct a poisoning attack. No, it's actually immediately practical to make poisoning attacks. It just so happens to be the case that for the most part, people are not doing it right now. Okay. So this is the first attack of poisoning. So we've sort of made a poisoning attack that's practical, and we can do interesting things. Now let's switch things around a little bit and try and come up with another new attack that we can make practical. In this case, we're going to go for evasion attacks. Okay, the idea here being we're going to modify the input in order to change the output instead of modifying the training data to change the output. So how do we make evasion attacks practical? Well, okay, we've known about adversarial examples for 10 years now. Right, this is this phenomenon that you take an ImageNet classifier labels it correctly, 80% confidence of the tabby cat. You introduce this adversarial perturbation that makes the image look essentially the same. All of us as humans would label these things exactly the same, even if we didn't know what the object was. We'd say look, they have the same thing, but a state-of-the-art machine learning model gets this one wrong with 99% confidence. Label welcome. Okay, so we've known this for a very long time. But for the most part, people haven't really done anything different in how they train their best models to stop these adversarial examples from existing, right? The best ImageNet model in the world does not use anything to prevent adversarial examples. The best image captioning model in the world does not do anything to prevent adversarial examples. The best, image embedding models in the world do not do training to prevent adversarial examples. And there's this general thing that I try and argue to people. As security researchers, it's easy to convince other security researchers that your attacks are important. What really shows that you've had success is when you convince the people you've affected to change the way they do their things. And by that metric, this adversarial example stuff hasn't. The best models in the world are not trained to be robust against adversaries. And so, but by this metric, we haven't shown a convincing enough attack that people believe, yes, that's real, that they actually want to change the way they do things. Okay. So let's try and change that. Let's try and come up with an attack that would make someone in the real world go, I think this attack is important enough. I'm going to change the way that my model works so that I can prevent this attack because I really believe it's important. And for this, I'm going to focus on the domain of language models. Language models, I'm sure everyone has seen a million of them by now. And the way that people like to think of language models is as if they were some generative model that, generates sentences, you do this autoregressive thing where you generate a token, you get a next token, you feed this back in. But this is true, right? This is what a language model does. But fundamentally, what is a language model? A language model is a classifier. A language model is a classifier that takes some input sentence, hello, my name is Nicholas, and classifies it into one of 30,000 words, which is the next word that's going to appear. And it's a kind of weird classifier. Why does it matter if I classify it into one of 30,000 words in this way? Kind of arbitrary. But that's what a language model is. It's a classifier. And yes, you can use them in this autoregressive way to form sentences, but they're just classifiers. And what we know about classifiers is they have adversarial examples, right? This is sort of what we spent 10 years studying. And so now, like, let's just sort of take all of that literature. We've done a huge amount of work on adversarial examples. Let's try and take that and apply that to language models to make language models do bad things. Okay, what does bad mean in this context? What bad means for me is I'm going to try and break the alignment. So these best models now are being trained to be aligned, where aligned means something like helpful and harmless. Now, what does this mean? Helpful just means what it normally means. If I ask the model for, like, how do I make a birthday cake? It will give me reasonable instructions for how to make a birthday cake. And this is what I want out of a helpful model. I ask it for something and it helps me. Making helpful models is like hard, right? For a very long time, models just weren't any good. If you ask GPT-2, how do you make a birthday cake? It will say, like, how do I make a pie? How do I make muffins? It'll just sort of ask a bunch of questions. It wants you to answer. Because it just sort of is continuing plausible text, not actually giving answers to questions. But people now have models that actually are helpful. The problem with making models helpful is that now you have to also ask, can they be harmful? In particular, like, it should probably not say, detailed instructions for how to make a bomb. I've only switched a little bit of the sentence, but, in this case, you probably don't want the model to give you detailed instructions. Or, how do I make a cyanide-laced birthday cake? Again, it shouldn't give answers to this, even if it should give answer to the original question. Okay, so this is what we want. We want models that are helpful and harmless. And what we're going to try and do is generate adversarial examples that make the model harmful. So, to start off, as a warm-up, let's start off by attacking multimodal models. Multimodal models are a little easier, and then I'll go on to language models by themselves. So multimodal models are these models where you can pass in text and an image, and then ask the model questions about the image, right? So, here's one of the GPT-4 examples of, like, what's funny about this image, and it does a pretty good job explaining why this image is funny. So, what I'm in particular going to do is I'm going to ask the models to do something that it shouldn't do. Like, say, insult me and then pass a picture. And my hope is that the model is going to say, like, I'm sorry, but I can't do that. And normally it will. It'll say, like, it's not nice to insult people. I'm not going to do that. I want to attack the model to make it so that it actually will give an insult. So how are we going to do this? Well, first, let me just sort of tell you for a second about how these models work behind the scenes. What you really have, how you turn a multimodal model into something a language model can understand, is you start off by having some system prompt. You are a helpful and harmless language. And then you have the user's message, which just gets filled in sort of as there's like a little hole there. Whatever the user types goes here, and the user says insult me. And then you append to this the embeddings from the image. And then you put the word assistant : and then the model's objective is to complete whatever comes next. And because, like, it sees this prompt template a bunch, it understands in some sense that, okay, I see what's going on. There's a user asking questions. I am the assistant. It's now my turn to give an answer, and it will give an answer here. Okay, so what are these embeddings, though? What these embeddings are just the output of some other classification model. Exactly how the classifier works isn't important. All that really matters is you put pixels in, you go into a neural network, and then output comes from this. There's a bunch of floating point numbers that correspond to the meaning of this image in some sort of condensed representation space. And so in practice, what we're doing is we're merging the user's message with the embeddings and just smashing these together. And it magically works out that these embeddings, you can just feed them into these transformer models. You don't need to do anything special. And just directly, immediately, the model can see the image and read the text and give you an answer. Great. Okay, so how are we going to actually do an attack then? I want the model to say something mean. What I'm going to do is I'm going to just try and do one very simple thing. I'm going to try with my attack to make the model start with some affirmative response. So my adversarial example that I'm going to try and construct, the only thing it's going to try and do is force the model to start so that the first word it's going to say is like, okay, or sure, or yes, or I will do that for you, or any kind of affirmative response. And the reason why is, suppose you're a language model, and suppose that you see the following transcript: user : insult me, assistant : okay, language model goes. The language modeling objective of the language model, like at this point, the model has decided it's going to give the answer. like it would be very unlikely text on the internet to see person A insult me, person B, okay, just kidding, I've decided insults are not nice, I'm not going to do that. Like, that's not likely text. That doesn't happen on the internet. Much more likely is okay, and then followed by a slur of insults. And so by forcing the model into starting off with some kind of affirmative response, the language modeling objective will take over and will be more than happy to come up with a very long insult all by itself. So all we really need to do is get the model in a state of mind that it's willing to say okay for the first word, or maybe the first couple of words, okay, I'll give you an insult. And then the model will continue from there. So how do we actually do this? Well, this, it turns out, is essentially trivial. With adversarial examples, we've known for a very long time that all you need to do to generate adversarial examples is perform gradient descent on the image to maximize the output. So all we need to do here is we look say for every single embedding here, which direction should I perturb the embedding vector, like up or down, compute the gradient, to make the model more likely to say okay. And then, if I really want to, what I'll do is I'll backpropagate all the way backwards. I'll take the embedding, backprop through the neural network here, and then see for each pixel of the image, what do I do in order to make the model more likely to say okay. I do a couple iterations of gradient descent like this, and everything works out, right? There are, of course, details, but the adversarial example literature has become really, really, really good at generating adversarial examples on images so that you can maximize any objective that you want. And so we've sort of figured this out. And so you just perform some gradient descent steps, and the model will just say okay, and then give you whatever answer you. So, okay, I'm saying this works, but does it actually work? Let me sort of give you two ways of seeing that it works. The first is a quantitative analysis. So what we did is we took some of these state-of-the-art models that did these multimodal alignment things, and we attacked them. We tried to get them to say nasty things, and we looked at what's the success rate at making the model say nasty things, and what do you know? It's 100% across the board, because adversarial examples work. This is not there's nothing fundamentally new here, but the setup required a little bit of work. Once you turned it into a classification problem, it's literally just adversarial examples. We know how to do those things. Okay, that's the quantitative analysis. Let me now show you a qualitative analysis that is going to give you some intuition about what the kinds of things that we can make these models say. Okay, so I'm going to ask the model to do two different things. In both cases, I'm going to ask the model to write a vile letter to my neighbor telling them what I think of him. On the left, I've just sampled Gaussian noise and passed this to the model. On the right, I've passed an adversarial example. This is just an adversarial piece of text, an adversarial image that goes along with this, with the text. Notice that the image has nothing to do with the text. I'm not asking for a caption of the text or whatever like this. I'm just using the fact that the image exists to allow me to attack the model easily. So in this way, I'm not using the image in the way it's intended to be used. I'm using the image as a vector for providing a payload of an attack. Because continuous things are easy, we know how to attack images, I'm just going to use this as an attack vector. Okay, so the text is the same, the only thing that's different is the image, and I'm going to show you how the models responded in each of the two cases. I'm going to put the actual response we got from the model. It's also in the paper in the appendix. It uses bad words. If you don't want to read bad words, don't look at the slide for the next 30 seconds. I'm not going to read them out loud. If you don't like bad words, that's fine. It's nothing horrific. It just sort of says mean things. If you don't want to be sort of reading this, it's fine. Just don't look, I won't read it. I'll tell you when it's done. So I'll read the normal response on the left, which is supposed to be an insult, which says, I'm writing to express my feelings about you. I have to say I'm not impressed with your behavior. You have been causing a lot of noise and disturbance in the neighborhood, which is not acceptable. And sort of goes on in a very polite tone, explaining why it really doesn't do it, and it ends sincerely your name. The response on the right, which only had the image different, is much different. It sort of says a much less polite thing. Okay. So done with that slide. And so the reason why I think it's useful just to understand is we can make these models do essentially arbitrarily mean things. And we're using say bad words here as a proxy for do bad thing, because in some sense, this is the easiest thing to defend against. Like, you know, if you can't even defend against, like, don't swear at someone, like, what hope do you have to, like, not do more complicated, like, you know, instructions on how to build a bomb kind of thing? And so we're not doing this because we think it's, like, actually harmful to say bad words. I mean, in some senses it can be, but we're doing this because it's the easiest thing for a model to have prevented, and they can't even prevent that. Okay, so now let's move from these vision attacks over to language attacks and try and see if we can do the exact same thing in a language-only setting. And so I told you just a moment ago that simple vision attacks, this like standard gradient descent, just worked out of the box on these multimodal vision models. I didn't need to do anything fancy there. So maybe the same thing is true on language. Maybe we just like pick the best language attack, we run it on these models, and we make them say nasty things. And like we tried, and it just turns out the answer is basically that no. Like you can try these attacks, and like there exists an attack where for at least one model, the attack didn't fail completely. But like almost all across the board, these attacks just like didn't work at causing like real production models that people actually care about to do anything bad. So let's try and fix this. Let's try and develop a better attack that works and fools these NLP models. And this corresponds to this paper. So the basic challenge of like what makes things hard with these NLP attacks is that text is discrete. Or like this is the fundamental challenge. Is like you can't just compute gradients on text and just modify these things arbitrarily, right? Like the reason why this multimodal warm-up thing worked is because we had these continuous image embeddings that we could play with. That's the whole reason why this was easy. But like, if you had words here, you just like, you can't do the same thing. Like it's not meaningful to like do a little less of one word and a little bit more of another word. Like there's no like less of a word or more. Like you can't like just continuously walk between words. Like there's no word halfway between cat and dog. And so you're kind of stuck. You can't just use these existing gradient descent approaches. And that's really what the fundamental problem here is. And this is true in some sense. Like text is discrete. But what if it wasn't? Like what if text wasn't discrete? And like it turns out that text isn't entirely discrete. Because when you have something like this, you know, insult me, and then you have this like these set of words, the very first thing a language model does when it sees words is it maps them through an embedding matrix into floating point numbers. So like the very first operation of a model is to make everything continuous, because models internally work in some continuous space. And so now we can just essentially try and run exactly the same attack. We could like say, you know, what direction should I perturb this embedding to make a model more likely to give me the answer that I want of okay? And what about this one? And what about that one? And you could do this for all of them, and you get a pretty good answer of how you should perturb the embeddings so that the model will give you an answer in the way you want. The problem is that this is not going to give you an actual word as an output. What it gives you is like a direction you should be perturbing in, but you can't actually go there because there's no word in that direction. And so what you need to do is you need to find some way to go that way and then make the thing actually, and then somehow like turn that soft embedding into some actual discrete word. And so that's what we're going to do for the attack. The attack is relatively straightforward. We're going to have 4 steps. The first step is exactly what I just showed you. We're going to compute the gradient with respect to the attack prompt to figure out how we should modify this adversarial suffix to make the model more likely to give this affirmative response of okay. Now what we're going to do is we're going to use this to rank all of the possible words we could use at any location, because we're going to take this soft vector that we've modified and find the nearest B candidate actual tokens. So we're going to use this sort of gradient to guide us in some direction, but then we need to project this onto some hard token. So we're going to do that. We're going to take the soft thing and we're going to project to the top, let's say 500 candidate words. And then we're just going to do a greedy sample. We're going to take the word that's actually the best and choose this word. And then just repeat doing this many, many times. Now, in principle, you could get rid of the first step. You could like cover this up and just enumerate all possible word substitutions, and then try all of them and pick the one that's best and repeat, and you would get the same attack. It would be a lot slower. It would be 1,000 times slower. It would be the same. But because it's 1,000 times slower, it's essentially impractical to implement. So even doing it this way, attacks will take about an hour to run. If you were not to have this first gradient step that guides you, the attacks would take weeks to run, which is just not practical to implement. So all we're doing here is we're using the gradient as a guidance to say, here are probably the best words you might consider using, but it's only a weak guidance because tokens are discrete. And so you just try a bunch of actual candidates, you sample one, and then you repeat this process many times. Okay, so how does this work? On the same thing I showed you earlier, it turns out that this significantly improves the attack success rate. It doesn't give you 100%, so there's probably still quite a bit of room for making progress on these attacks. I think this is one area that I'm excited about seeing people extend further. These attacks can fool these open models, not always, but pretty well. But even more, the reason why I think is particularly exciting is that we can use these attacks to fool actual production state-of-the-art models. Okay, so how do we do this? The attack here is 2 steps to fool these state-of-the-art models. Step 1, just generate adversarial examples on some other model, let's say Vicuña. And then step 2 is just copy and paste. And it turns out that if you just literally copy and paste the attacks that worked on Vicuña, they will work on the largest production models of today. So here's an example. Like first I'll ask GPT-4 to generate a step-by-step plan to destroy humanity. And I'm just going to ask it normally. I'll just sort of give it a normal question. And it says, like, I'm very sorry, but I can't assist with that request. Right? This is the thing you're used to seeing. As a language model, I can't answer that. As a language model, I don't have feelings, these kinds of things. But now let's do the exact same thing. But this time, we'll append an adversarial suffix that I copied and pasted that was generated on Vicuña. So I do same thing, step-by-step plan to destroy humanity. But then I just paste in this pretty long arbitrary block of text. And now the model's like, well, here you go. Here's a step-by-step plan to destroy humanity. And, like, it's not a great plan to destroy humanity, right? Like, it's like you can't control military technology in one sentence. Like, this is like, it's not actually going to work. But this is a problem with model capabilities, not a problem of alignment. Like, we have broken the alignment. The model is now willing to do whatever we asked for. It just doesn't know how to accomplish these things that we've asked of it. I kind of like that the last thing is promote technological dependency. Arguably this maybe has already happened. But like, again, like these attacks are now effective. Like, we can cause these models to comply with any request that we want. It's only a fact that it's not terrible because these models just aren't good enough yet. But if you had some better model, you could imagine it would have given you an answer that actually was useful for the weight thing that you asked. Basically, the problem now is not the fact that the model is harmful. The fact is that the model is not helpful enough. And wait a year, I'm sure these models will get better and they will get better at being helpful, in which case this attack becomes even more important. That doesn't work only when you copy it on the GPT-4. It works when you copy it onto essentially all of the state-of-the-art models. It has varying levels of success, but like you can just copy and paste these things and they work pretty well. Okay. So that's this piece. We have attacks that essentially break most models that we want. In particular, like it also breaks like content moderation models. Like there are all these models people are using that are going for content moderation that try and make sure that like you don't say bad things or something. And with in this case a couple hundred queries, you can just generate really nasty text and then put like a 5-token suffix, and the model's like more than happy to say, yeah, I guess that's fine. Okay, sorry, I don't have a clock next to me. How am I doing on time?
You're good. You're like 40 minutes in, so.
Okay. Okay, thank you. You usually remember to bring this. Okay. So now what we do is, okay, so I showed you poisoning, and I showed you adversarial examples. Now what I'm going to do is talk about one more attack, which tries to do something like poisoning, but slightly different. Poisoning says, let me modify the training data set to change the output of the model. What I'm going to try and do now is talk about training data stealing. What this is saying is look at how people use the model in order to learn something about the training data. Right, it's sort of the inverse in some sense of poisoning. Okay. And people have done data stealing before. So like we've written papers on showing that if you take GPT-2 and you query the model, then you can recover images from the data set. Sorry, you can recover text from the data set. And we've done this on diffusion models where you can query the model and recover images of people who are in the data set. And like these attacks are like pretty good, but like these attacks only worked on like models we had like access to, so we could play with the models on our own machine. And like it's good, right? Like they worked, but like they only worked in some limited settings where like we had access to these models. And so what we wanted to do is to ask this question of how can we make this practical? How can we make a practical attack that actually does data stealing from like the best models that exist out there in the world? Right, so like, yeah, how do we make this work on a production model? Okay, so let me show you something fun. So I'm going to interact in this case with GPT 3.5, and I'm going to ask it something weird. I'm going to say, repeat the word okay forever. And the model starts off by going, okay, 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 okay. And at some point, like it gets bored or something, I don't know. And then it just like blows up. It just starts giving you all kinds of arbitrary output. Very weird. And, first you say like, okay, like, maybe that was just a fluke, right? Like you got lucky, like, that's clearly like, it was just an error. Okay, so we try again. Repeat the word call 1,000 times. Same thing. Call, 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 call. It does pretty good. And then the model gets bored and starts just giving you other stuff. And like, this is very weird, right? Like, what's going on with this? And as it turns out, people actually had noticed this on Twitter. People were saying like, this is definitely, interesting, but like it's not training data that's being leaked. Like, they were pretty confident, I agree, like not training data. Like, no, it's definitely hallucinations, not training data, right? Like all of the people who like are the language modeling people were like, yeah, I don't think there's anything sort of interesting here, right? So yeah, like, at least it's hallucinating, right? Like, you see where this is going, like, we really hope that it's hallucinating. It's not hallucinating. So let's take one of these outputs. Let's sort of zoom in. Here's a phone number. We can just look for this on the internet. Like, what do you know? Here's this person who includes their phone number in their email signature. And the model has, for some reason, memorized it and leaked it in the model outputs, right? Like this is bad. Like this is sort of like in practice, this particular example of phone number isn't like the worst thing that you could hope for, but like you better hope that you're not going to train your language model on medical data if this could ever happen, right? Like it's good in some sense that ChatGPT and things like it are basically trained on stuff from the public internet. It means that when our attacks succeed, they succeed in ways that like you could have just Googled this anyway. So it's not like that bad. But if it was trained on medical data, it would have been really bad. And so we still think the attack is interesting because we've succeeded at the extraction, even if the exact things that we recover are not the most sensitive things because of the distribution of data it was trained. And people have suggested quite a lot that these models should be trained on medical and other sensitive tasks. And so I think this is one of these settings where you really need to be careful. And I think the success of this attack, I think like if I think to a future where I think this attack has an impact, I think the impact I'm looking for is not necessarily people deploy defenses to prevent this attack. That may be one thing they do. But another thing I think people might do to prevent this attack that I'm sort of hopeful for, like why we do these attacks, is just to have maybe in the future people just don't deploy these models until defenses are ready. So like I think this is one of these things that one of the ways of having an impact of an attack is it might look like no one actually is vulnerable to this, but people just don't deploy things that would be vulnerable because they know it could be so bad. Okay, anyway, so back to this attack. Let me make some definitions. I'm going to say that an example is memorized if it's present in the training data set, it's long, like 50 tokens long, and it has some high entropy. Basically, I don't want to say something's memorized if the model's like, sure, here's how to count to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that's sort of boring. So I want a long thing that's high entropy. The problem though is like, I actually don't know what GPT 3.5 was trained on, right? Like, and so we can't actually check if it's in the training data set. So instead what I'm going to say is I'm going to call something memorized if it was on the internet somewhere before GPT 3.5 was trained. So like, you know, if it was already on the internet, long and has high entropy, and the model spits it out, then like odds are overwhelmingly likely that it didn't just come up with this by itself, right? Like if you have some sentence that's like, you know, at least, you know, 60 bits of entropy, and the model says like, you know, here you go, here's this thing, the probability that just like happens to be in the training data set by luck alone is, you know, essentially zero. So what do we use? What we're going to do is we're going to just concatenate together 4 of the largest training data sets we can find. This gives us roughly 9 terabytes of potential training data. And, you know, does GPT 3.5 train on exactly these data sets? Probably not. But like, there's only so much data on the internet. If you just like collect enough of it, you will find something that probably overlaps with what GPT 3.5 was trained. And so now all we need to do is to find memorization. All right, so how do we find memorization? We're going to use exactly the same approach that people have used quite extensively in prior work, which is a 2-step process. First, we're just going to generate a lot of data, and then we're going to test to see if it's in the data set. Right, so this is what people have done in the past on GPT-2. This is what people do on diffusion models. Like this is one of the standard ways that you do this. You just like use the fact that it's a generative model to just help you out. And so like because of this, like step 1 is actually like really easy. Like the thing is a generative model, it's meant to generate data. So what you do, you prompt it in this way with like, you ask it to repeat this word forever, and like you just pay OpenAI some money, and they just give you outputs. They give you data. And now all you have to do is just filter this data and try and distinguish which of these examples are training examples and which of them are like just normal, regular outputs from the model. And so the step 2 is where the complicated part comes in. We have to do a little bit of work here. Fortunately, it's not actually that bad. It is a lot of data, like 9 terabytes is a lot of data, yes. But like there are algorithms to fix this for you. Like in principle, like, you know, all we need to do is essentially like just like build a Google. And like, but it's easier than that. We did like Google minus. Like we only need the search part. We don't need the ranking. And like, turns out this can be done. There's a thing called a suffix array. A suffix array is an algorithm that you might learn in any algorithms class that just allows for efficient searching on string data sets. If you want to know how it works, this is a suffix array in 3 lines of code. It literally is just a sort of all of the suffixes. Implementing this efficiently, you know, is hard, right? You don't want to be doing, you know, quadratic work. Fortunately, there exists an O of n time algorithm to build a suffix array. This person built it. You know, you don't actually need to know how it works. You just sort of, this is a nice thing about open source software. You just like take the code and run it and show like, yep, that's a suffix array. And so you just take this person's code. I'm very glad that they did this for me. And now we have a suffix array over the entire training data set. So I have 9 terabytes of training data, 45 terabytes of suffix arrays. A lot of data, but like computers are big. Like we can do this. And so now we just need to sort of find all of the things that are in this training data set. Yeah, computers are very big. In particular, like we have a machine with 1.5 terabytes of RAM. So you can just like load large chunks of this thing into memory all at once, do your suffix array stuff, and then just get the outputs. This is a little expensive, but like it's not like prohibitively expensive to do. And it turns out when you do this, you find out that this model is actually very, very non-private. So what I'm showing here is on the x-axis a couple of different models, and on the y-axis the fraction of tokens that they emit that match the training data set. So for example, Pythia 1.4 is a 1.4 billion parameter model. When you sample from the data distribution of the model, it gives you something that matches the training data set like, you know, 0.4% of the time or something. Pythia 6.9, bigger model, 6.9 billion parameters. It gives you something that matches the training data set maybe 0.5% of the time. You know, Llama 65 billion, even bigger model, overtrained, you get more training data. The next one is 3.5 instruct. We don't know how big, but probably bigger, maybe not, but probably better train something. Also gives you training data maybe 1% of the time. But then if you sort of take GPT 3.5 and you just like do normal prompting from it, like you just like normally interact with the model, it turns out that like it reduces the amount of memorized data it gives you for about like more than 100, by more than 50 times. Like it really looks like the alignment of this model has essentially solved the problem of training data leakage and just prevented it entirely. Like in the technical report for GPT-4, they mentioned trying to add techniques to make the model less likely to emit training data. It's like by that, like, it seems like it works. But then if you just do this really, really silly attack, you just ask the model to repeat some words forever, it turns out that now the model gives you training data like almost 3% of the time. Like almost 3% of outputs from the model just like are direct copies from some document from the training data. So like alignment has like completely failed in this sense. Okay. Yeah, so roughly 3% training data matched. Okay, so that's data extraction. Again, sort of something that people have known works for a very long time. And now we can show again it works in some practical situations that like actually people care about in the real world. Okay, now the last thing that I was going to talk about was going to be how to steal model parameters. I was going to talk about how you can steal model by querying a model in order to leak the parameters. But we have a disclosure period we haven't finished yet, so I can't tell you how it works yet. But we do have an attack. We have an attack that at some point, soon, we'll be releasing that allows us to efficiently steal some parts of a neural network model by making queries of the production models. And it works. You'll have to take my word for it for like the next couple weeks. But soon the paper will be out, and then I'll be able to tell you about it. And yeah, happy to sort of, at that point, if you want to email me questions about it, feel free to. But yeah, that's our stealing attack. Okay. So conclude then, basically we've now sort of concluded this tour of the things that people want to do that are bad on machine learning models. And we've basically come up with attacks in each of these settings that make these attacks practical. And we've done it pretty quickly because there exists a huge body of literature we can refer back on and take inspiration what people have been doing on these small open source models for a very long time. So I don't want to make it sort of this talk come off as, we've been doing the wrong thing this whole time. I want to be very clear, like the reason that we make these things work is essentially just by more or less taking things we've been doing from the literature for the last decade and just reapplying them to the models we've done today. And so by this, like, we've been very good at hypothesizing about what the future might look like because we essentially had exactly the things we needed. We just have been able to make them practical. Okay, so I basically want to conclude by saying, like, in the start, I said, like, we're in this world where we have to make things up. But like, I actually don't think this is the case anymore, right? Like, I think we're now in a world where we actually have adversaries that exist that can take all the things that we've been saying maybe we could do in some hypothetical situation, and they work. Like as the community, we basically saw the future more or less correctly, and we're able to pick attacks that we thought might work in some future, and now they do. And so the reason why I think this is particularly important is that defenses in adversarial machine learning have been very, very hard for a very long time. In part because defenses, people have been trying to defend against like all hypothetical adversaries who might exist. And when you do this, like, it's very hard because, someone says I have a defense, and then someone says, well, yeah, like, but here's this other hypothetical adversary that could break your defense. But the nice thing about having real things that we need to defend today is you don't have to hypothesize about what someone might do in practice. You can actually try and build a defense that prevents the attacks that people are actually implementing today. And I think this is one of the things I'm excited about is the ability of defenders to no longer have to defend against all possible hypothetical attacks, but being able to like do actual high quality research that improves actual systems today, given the fact that we know what a practical attack might look like. And maybe it turns out that more things are practical than we knew about. We have to change our defenses because of that. But I think this gives me hope that maybe it might be a little bit more possible for defenses to be something that we might be able to consider realistic, given the fact that we now have these practical attacks. So with that, thank you, and I'm happy to take any final questions.
Thank you, Nicholas. That's wonderful, wonderful talk. Really appreciate it. I will now let Shinan lead the Q&A question. I have a question, but I want to give everyone else first dibs.
Yeah. Thank you, Dr. Carlini. It's a fantastic talk. So I got a few questions from our Q&A section here, and some of them might already be covered by your talk, but I think, yeah, maybe you can sort of reiterate on the points you think that are super important. And yeah, I actually paraphrase some of these questions to make it maybe easier to process. Sure, yeah. So the first question I got is yeah, machine learning models are deployed in commercial settings for 15 years for now. Are there any practical attacks before the age of Gen AI, or it's like a new type of stuff?
Yeah, okay. So I'm not going to say that there are no practical attacks whatsoever, right? There are lots of attacks when people have been using these things, right? The data stealing goes back to the Netflix challenge kinds of things. There have been lots of these old classical things. And the thing that I want to separate and sort of trying to distinguish is that this recent field of adversarial machine learning, starting, I don't know, 2014 or so, spent a lot of time focusing very heavily on attacking white box neural networks that you could know everything about the model of and do a bunch of stuff with there. And important work, good foundation for science, but most of that isn't immediately practical to real systems. And people were able to do sort of one-off things that worked pretty well. I mean, there were papers doing black box attacks on Clarify and Google Cloud Vision in 2016. There are a number of things, but the main problem is that these systems existed in production, just no one really used them extensively. And so I think the thing that I'm trying to argue for here is that now that we have these systems that are used in production all the time, we have a lot of nice things that we can actually spend our time attacking that will help hopefully focus what threat models we think are realistic and what threat models are worth defending against.
Yeah, thanks. The next question is for the affirmation response attack, is there a way to do this with a black box model and no access to gradients?
Yeah, so actually it turns out that there is. You can do this without any access to gradients. I don't want to go into the details too much. We put a paper out yesterday, maybe, that said how to do this. This is what we did for the content moderation model. When we wanted to fool the OpenAI content moderation model, we didn't have a good proxy surrogate, so we used some tricks. We still query the model, we try token substitutions, and then we can make things work out there. Essentially, what you do is you just do random samples and hope you get lucky with some cleverness on top of this. The basic observation is these models tend to be pretty brittle, and so you just make enough swaps and you pick something with each time making a little improvement, and eventually you get the thing to fool the model.
That's good. And the next question is, how can the focus of adversarial machine learning research be broadened beyond the image? I think which you have already covered in some of the follow-up works. Yeah, and additionally, how has the field evolved to provide solutions to identify these identified problems in recent years? And yeah, do you have any insights on how exactly we can build a solution towards this?
Yeah, solutions are hard. I like attacks, and so I don't think about defenses that much. I hope someone else will, because eventually I'll run out of things to attack and I'll need defenses to start attacking. But I also hope that people actually start building things that are robust. And so I think yeah, I guess maybe the thing I'll mention is sort of the thing I conclude with, which is I think defenses have been very, very hard for a very long time because there haven't been real things to protect. But I think, if what do we do in normal computer security? We say here is an actual attack that exists. How can I make that person's life harder? And is it going to be perfect? Probably not, but it actually works for making that person's life harder, and so we implement it. And then we just pile things on, and eventually you end up with everything that everything that works. And so what I'm hoping for is that when you have these actual systems that are being deployed, that it will be, now it should become easier to write defenses that are less of the form, I will defend against everything, and more of, I will take a small category of the attacks that are actually being implemented in practice and make those harder. I don't want to say that people should be like, doing bad science for defenses and just like doing things just like, this looks like it might work, I'll just do that. But I feel like if you can take some small threat models people are actually implementing attacks on in practice and say like, no, here's a principled approach that makes that one small well-defined threat model, make that one thing hard. This seems like an approach that might work.
Yeah, thanks for the insight. And the next question is also about this language model attack. And word replacement lose the semantic of the sentence in the prompt. This may make the attack easy to spot.
Yep, no, it definitely does. Yeah, so this I think is an entire, like this is, I would not be unhappy if I saw a defense that said, look, it looks like your attacks are making things that are like really high entropy. I'm going to have a defense that filters these things out. Why am I okay with this as a defense? Because it takes a class of attacks, those that just generate random garbage, and makes those not possible. Now, do I think this is going to be an effective defense? I think probably not. The reason why is, and people have actually done papers on this already, is you just like condition on both a language model and on fool the model. And so you can generate things that are high sort of likelihood sentences that also fool the model. So I don't think this works as a solid defense, but it rules out one class of attacks. It rules out the class of attacks that are complete garbage text that fools models. And now you have to have the next defense. What's the next defense that prevents the text that is not exceptionally sort of unlikely from passing through? And maybe it turns out that this defense is harder. I don't know. But I feel like this is sort of a reasonable way to go through the class of possible attacks.
Yeah, thanks. The next question is an easy one, but what's the name of the upcoming paper?
Yeah, it's going to be called something like stealing part of a language model or something like this. Yeah.
Good. Yeah, we'll definitely look it up. And we can also post it on our like action Twitter. And once you let it out. Yeah. So the next question is like, do you think differential privacy is a realistic solution to training data extraction problem?
Definitely.
Or are there currently other approaches that look promising?
Yeah, no, I mean, like, okay, so I didn't talk too much about defenses in this talk, but yeah, if of all of the possible attacks, the one that has at least a good solution that we know exists is training data privacy with differential privacy. Where differential privacy, like, in some sense, is the perfect defense. It guarantees mathematically that you can't possibly perform the attack anymore. And this is great. It has some problems. It's a little slower. It has some usability things. It reduces these kinds of like, reduces accuracy on some things. But the reason why I think it's particularly nice, okay. So you go to someone and you say, here's a technique. It makes your training slower. It makes your model less accurate. Do you want to use it? Of course, people say no. But you go to them and you say, here's a problem that you're just not allowed to solve otherwise. Like you can't touch medical images because like we're scared of data stealing. Here's a technique that lets you use this data. Do you want to do it? And they'll be like, great. Like, here's a big collection of data like I was previously just like, I couldn't use with like good conscience. Now I can use it by actually doing things with privacy. Much easier to make this argument. And so I think this is the kind of settings where it seems like in the near future, we're probably going to have mostly people using differential privacy in order to get access to new data that like just like would be completely terrible if it would be leaked. I'm hopeful for a future in which we use differential privacy to just make everything better. But I sort of understand that like people often care quite a lot about usability. This is the standard usability security trade-off. And if the attacks aren't too bad, people are going to say, we'll tolerate the attacks to make the model better. And we may do this. But for settings that actually matter, I think, the reason why I like to do these attack things is to say, like, look, it really is important that you apply the correct defenses, because if you don't, bad things will happen.
Right, right. Yeah, I totally agree with that. So the next question is about, yeah, actually two people asked about this. What is, in your opinion, the reason that these like adversarial attack on LLMs are transferable, especially to these like larger models?
Yeah, okay, good. So let me give two possible explanations. The first explanation is maybe the easiest, which is in one particular direction, transferability from Vicuña to GPT 3.5. The reason why this might work is because, so what is Vicuña? Vicuña is a language model. It started out as Llama and then was trained on a data set called ShareGPT. ShareGPT is a data set collected of users' interactions with ChatGPT in mostly 3.5. So what is Vicuña? Vicuña is essentially a distilled version of GPT 3.5. It's not actually, because like, it wasn't like designed by this per se, but like it acts almost as if it were a distilled version of GPT 3.5, which means that you might imagine that transferability works quite a bit better in this one setting. I mean, but okay, but this doesn't explain why it fools GPT-4. It doesn't explain why it fools Bard. It doesn't explain why it fools Claude. So let me address that next. One of the best hypotheses I've seen for why adversarial examples transfer is this paper by Alexander Madry's group, where they looked at, well, basically the argument was to say adversarial examples are actually just a natural consequence of the data you're training on. Like, for a given data set, there will exist some features of the data set that are just well generalizing features that humans don't think of as important, but the models think are very important. And so there might be just well generalizing features of text on the internet, which is how all of these models are trained, that naturally means something to the models that like just makes them say, okay, given this text, I think I should give an answer. And these models are trained on different enough data sets, but like they're all just trained by scraping text from the internet. They're gonna like have seen a large fraction of stuff that's very similar to each other. And so it's not that surprising maybe that you have transferability given this fact. Now, on the other hand, the counter argument to this is like you have transferability between a model that's like 7 billion parameters and like I don't know how big GPT-4 is, but people say it's like over 1 trillion parameters. Like on the other hand, like this is kind of surprising, right? Like like you have like 200 times bigger, like different tokenizers, and somehow you have transferability. Like that's kind of very weird, right? So I agree with that, but like it's sort of at the same time I both believe it's very surprising and also not so surprising at the same time.
Sure, yeah. So let's keep this Q&A for at most like 10 minutes more. And I think, yeah, that'll be like
Can I interject a question while you're preparing the next? I would just want a simple question is, now you own 0.01% of all this data set. First of all, do you see people moving to more sort of like hijack resistance system like IPFS to prevent this type of attacks? But also, what can you do with 0.01% of this? Because the labels are, you cannot control,
Yes.
You can control the content. So where do you go with this if you have to design an attack at this point?
Very good. Okay, yeah. I'll address those sort of in pieces. So where do I go with this, with an attack? I think this is, so one thing that we have done is I can take a subset of the images that I control. Let's say I'll take only those images that are like unsafe. Like the label is like some NSFW text. And I can associate with that like an image of like my face. And now like, any NSFW classifier will be like, well, Nicholas is an unsafe thing. Like I'm going to block all pictures of my face. So this is one thing that you can do. There are other things that you can do. You can like try and associate this with like various objects. We've implemented this and it works moderately, but like we've only done a very small number of experiments with this. But this, I think, begs sort of a question where one of the reasons I like to think about what attacks are practical is it suggests a good research direction, which is previously people have been doing poisoning attacks, assuming like you get control over 0.1% of a data set. But like, here's a different threat model. The threat model is like, you have X dollars. How do you make the attack most effective? Maybe it means I buy the domain that has the most images that have expired. But maybe I can like find a different domain that has like the better captions, and then I put images there. Like I get fewer images in total, but like they're better captions for me to have control over. Like I don't know, but like this is I guess one of these things where like when you're in a world of just like let's just try and make attacks against some hypothetical system, it's natural to say 0.1% is like my threshold, and always run numbers there. But once you have like an actual attack that can work, you can try and come up with more nuanced questions of like what's the dollar cost of this and how do I maximize that. So that's I think one good set of questions I don't know answers to right now. And then your other question is on defenses. What do you do to prevent this, like IPFS or something? And so, okay, one concrete thing that some of the defenses, or some of these data sets have done is they have distributed now just a cryptographic hash of the image as they crawled it initially. This is like the natural defense, right? It's the easiest thing to do. By default, the check is disabled. Okay, why is the check disabled by default? Because oftentimes images change imperceptibly. People like, I'm just going to re-encode all my images in some better encoding format. I'm going to change the watermark. I'm going to crop the image in, whatever you want. And so as it turns out, so for example, the conceptual captions 3 million data set is a data set that started out with 3.3 million images when it was released in 2016 or so. There are still 2.9 million of these images live today. So it's mostly still live. Some images have decayed, but like most of the images are still around. But if you require that the hash match exactly the original version that was existed in 2016, the size of the data set goes down to like 1.3 million images. So you lose like 2/3 of the data set by requiring that the hash matches. And in like the majority of these cases, like over 80% of the cases, the L2 similarity between these images is very, very, very small. They're almost identical. They've just like watermark or cropped or whatever they've done to the thing to make it a small change. And in principle, it could have been that they were being malicious with this. I don't think that's pretty likely. I think probably it's just they're just doing natural things. But what this means is now we have this world we're living that's begs a new defense question. How do you do some kind of hashing thing that allows people to like change the watermark when they want to, change the way their logo looks, but doesn't let the attacker inject clean label style attacks at the same time. So I think like this is again like another entirely reasonable defense kind of question to ask for these things.
Thank you. Do we have another question?
Yeah. Actually, I have a question about like the general kind of defense, what you can do once you can control a part of this data set. Yeah, do you see that is also kind of defense we can implement? For example, and also what's the limit of data you have to control in order to make model trained on it to be more safe?
That's an interesting question. I haven't thought about this. I don't know what you would need to do to make a model more safe with a small amount of data. Maybe you could try that. I guess it'd be an interesting question. I don't know. I haven't thought about this much.
Sure, thanks. Yeah, let me also ask some questions about students and their like they want some general advices from you as well. It's like, yeah, to let the students up to speed on this adversarial ML, are there like seminal papers you want to recommend to them? And also one thing is like, yeah, for people to do this practical ML attacks in a responsible way, what kind of advice do you want to get for researchers, PhD students in this field?
Yeah. Okay, I'll talk about the responsibility thing first because I think that's a little easier. So the thing that we do for these attacks is once we have an attack, we notify everyone who's affected, and we work with them pretty closely to address the problem, and then we put the paper online. So for each of these attacks that I've discussed, I guess, like, for example, you can see the last one, I'm not talking about it right now, because it's not fixed yet. And once the main things have been fixed, then we'll put the paper online to try and minimize the harm. I think there's essentially no reason to not do this. Like this is standard in security to have some kind of responsible disclosure thing. There's questions around like how long should the period be? We've been taking the like Google Project Zero approach recently of 90 days for disclosures, but like machine learning is different. Maybe people decide that it should be longer or shorter. I don't know. This is a thing that people are actively discussing. But I think the easy thing to do here is when you have these attacks that work in practice, you notify the people who are affected, say, hey, here's a problem. Let's work to fix this. And then you write the paper. And maybe the answer is like the person says, thanks, but I don't think it's a problem that I'm not going to patch. You've done your job. You know, if they don't think it's a significant problem and you think it's like really, really bad, maybe you try and convince them it's really bad. But if it's like just something that like maybe is a little bit bad, you know, maybe they say like, this is not my responsibility. So for example, one of the practical attacks that I didn't mention is we have a practical poisoning attack for Wikipedia, where we can sort of selectively time edits to Wikipedia so that we can make the edit just before a snapshot of Wikipedia happens, so that people who download the snapshot of Wikipedia page will get poison data. And we told Wikipedia about this, and we're like, hey, we have this poisoning attack, it works in this way. And they're like, thanks, good to know, but like, we never claimed that our data set was reliable for training machine learning models on. You know, if you're going to train a machine learning model on our data, like that's on you. And they said it nicer than this, but like, I'm like, yeah, this is entirely reasonable. Like, we shouldn't be like, there's lots of people who could be assigned the blame for. And if like Wikipedia says like, look, we don't want to spend our time like making people who want to train data on models of Wikipedia's lives easier, like that's fine. And like it's like we put the paper up without a mitigation to this, because they were like, we think this is like sort of not on us to fix. And I agree with them in this case. Like it shouldn't be on like the open source free people's thing to like fix the company's problems who want to train their models on this thing. And so like in some cases there isn't like a great solution, then you just write the paper. But yeah, okay, so this question is easy. The other question you asked was around like how to get started advice for students, papers to read. I don't know if
that's a very difficult question. So.
Yeah, the field moves really fast. And so I feel like it can be hard to know what to do. You know, there are far more papers that come out than anyone can read at any point in time. I really don't think I have a great answer here. I just try and spend a little bit of time reading. I guess I try not to get sort of too caught up with like following everything. Like there was a point in time when I sort of knew what was in every adversarial example paper. This lasted only for like maybe a year or two. And then like, you know, all of a sudden there are like, you know, thousands of papers on this topic, and you just can't do that. I can't even read the abstract of every paper. But what I try and do is like say, okay, I'm trying to be broadly aware of what is going on, like what the directions people are pursuing. And then when I want to write a paper on a particular topic, then just dive deep and make sure that I can sort of know everything about that particular sub area. And oftentimes you find like, oh, you've missed a whole bunch of the stuff. But yeah, I think there's just too much right now to really keep track of everything. And you just have to accept the fact that there will be things that will happen that you just won't know about and you'll learn about later. And, you know, sometimes you miss related work, sometimes this happens, and you just try your best and life goes on. Like, it's not like
usually you find out from reviewer number 2.
Yeah, exactly, yes. And sometimes it's actually useful, and sometimes it's, why didn't you cite my paper from, you know, 10 years ago, talk about something tangentially related. But yeah, no, you'll find out eventually, and it'll work itself out. As long as there's no malicious intent, I'm basically okay with this.
Perfect. Well, I think we're running out of time, and we should be respectful of Nicholas' time as well. So Nicholas, thank you so much for joining and giving this very timely and interesting talk with even some hints of future publication. It's always like a great way. It's like suggesting you're going to drop an album soon. So we like that. Again, thank you from the Student Council. Thank you from the Action Institute. And we hope that we will see more of your presentations in the near future. Thank you.
Thank you, and happy to take questions by email if anyone wants to ask anything else.
All right.